We are now prepared to look at the concept of conservation of momentum. So recall that we'd been talking about a system of point particles, a well-defined closed system of, let's say, n particles. It's closed in by this dashed line that we show here, and let's say particle 1 has mass m1 and velocity v1, particle 2 has mass m2, velocity v2, and so on. We can define the total momentum of this well-defined closed system as p system equal to basically the vector sum of the individual momenta. And by applying Newton's second law in conjunction with the third law, we've seen that for such a system, the internal forces, that is the forces between the n particles inside the system, form third law pairs which cancel, so that the total force on such a closed system is only the external force, the total external force, and we've seen that the total external force is responsible for changing the momentum or the total momentum of the system. So in other words, we derived this equation: F external on such a system is the rate of change of the total momentum of the system, which is p system. What can we do with such a differential equation? Let's integrate on both sides with respect to time. Let's define this quantity, the integration of f external from times t1 to t2, and these should be vectors, of course, f external being a vector. Let's define this as the impulse between times t1 and t2 on the entire system. And we know, by applying the fundamental theorem of calculus, we know that the result of this integration is p system at time t2 minus p system at time t1. We can now ask the question, what if the net external force acting on the system is 0? Of course, in one dimensions, you would have the graph of f external, the magnitude of f external, looking like this. So the graph is 0. Obviously, if you integrate 0 between the time intervals t1 and t2, of course you'll get 0, right? In other words, if there is no external forces acting on this system, you have p system at time t2 minus p system at time t1 equal to 0, or p system, the total momentum of the system at time t1 equals to the total momentum of the system at time t2. And this is precisely the conservation of momentum. In other words, in the absence of external forces, the total momentum of a closed system remains unchanged. That is, for example, if you have a closed system like this of n particles, and you have no external forces acting on this system, then between, say, times t1 and t2, no external forces act on the system. What may happen is that the individual components of this system, being these n particles, the individual momenta of these particles can change, but this p system, which is the total momentum of this system, the vector sum, that does not change. So in the absence of external forces, you will have, if you have no external forces between times t1 and t2, then you will have the total momentum at time t1 equals to the total momentum at time t2, which is the conservation of momentum.